We can use similar techniques we just used when finding the centroid of shapes when we have a scenario where we have a distributed load acting on our structure. And a distributed load is going to be a load that's spread out over the length, a surface, or a volume. So it could be a 1D, a 2D, or a 3D loading. Until now, all the loads we've dealt with have been point loads acting at just a single point. Or in the case of moments and couples, it was just a point couple acting at a single point. A distributed load is going to be distributed, as the name implies, over our body. So things like water on a surface or snow on a surface. It could be the effect of magnetism acting in our 3D body, a wind load acting across the surface of a body, or discrete items like books or sand that's resting on our body. In all of these cases, we have a lot of loads at different locations acting on the body, but in total, it's going to have the effect of one load acting on the body at a specific point. So what we start with is we have to determine what the intensity of the loading is. So this is going to be the amount of force that's acting per length or per area or per volume. So what we can do is, if we know the intensity of our loading and we know how long it's acting on, we're going to be able to simplify this just like it were a area problem or a volume problem, so that we can find what is the equivalent load, which is going to be equivalent to the area or the volume of our loading intensity, and we want to know where we can put its equivalent point load, and it's going to be acting at where the centroid of that body is. This is how we are going to convert our distributed loads to an equivalent point load. And once it's a point load, we know how to deal with it just like we've been dealing with it with our 2D or 3D rigid body problems. So if the loading is going to have a functional relationship, that we have some intensity that varies along the length and we know the algebraic relationship between the two, then we can use our calculus, our one-dimensional integration steps, like we did for finding the centroid. Alternatively, if the loading can be broken down into simple shapes like rectangles, triangles, then we can use, like what we did for the tabular method, for those simple shapes we can break it down into where's the centroid of the shape, and that's going to be where the point load is acting, and we can find the area or the volume of the shape, and that's going to be the equivalent force that that distributed load is exerting on our object. When we make this simplification, externally the system doesn't know the difference. If we are finding the external supports and we simplify our loadings, the external supports are going to be calculated exactly the same whether we simplify it down to a point load or we leave it as a distributed load. So that's usually the first step of what we're interested in, finding those external supports. However, the system itself is not exactly equivalent when we reduce a distributed load down to a point load. Internally, the systems, when it's simplified and not, are not equivalent. And we're going to see this at the end of this course when we start talking about internal loads. This will be the bridge between this statics course and the follow-up course on strength and materials, where we're going to be concerned on what's happening inside all of our objects and finding the stresses there.